So welcome back to High School Physics Explained, and today is the third in a series I'm looking at in understanding the photoelectric effect. The first video looked at Hertz's experiment on radio waves and his subsequent observations of the photoelectric effect. The second video dealt with Max Planck, and this is the third where I specifically talk about the photoelectric effect. So if you've not seen those two previous videos, I suggest you do so. But let's have a quick recap. And if you remember from the previous video, Max Planck examined the black body curve. And the black body curve is a curve that represents the energy given off of a black body that is absorbing energy. And it has a characteristic shape. So that shape is basically infrared and light here over here. And as a result, this curve shifts as the temperature increases. It increases intensity, which is on this axis, and the peak moves more to the higher frequencies. But unfortunately, it cannot be understood in terms of wave theory. In fact, the Jean-Rayleigh law predicted that as temperatures increases, the intensity should increase infinitely into the X-rays and the ultraviolets and so forth. But that's obviously not what's observed, and that would cause a big problem. So Max Planck's solution was that energy is quantized, and that if you treat energy as coming in set discrete amounts, then mathematically you could actually get this shape. But which is all fine. There's the maths is fine. That fits the curve. But it didn't really fit in well with the wave theory. A short time later, a guy named Leonard did another experiment. And in this particular experiment, he set up this photocell over here and he fired light on it. And the light liberated charged particles or electrons. And he was able to set up this situation. He was able to set up measuring the voltage, and he could apply a voltage to it and also measure the current. And in doing so, the current, of course, is a measurement of how much charge is flowing at any one time, and the voltage allowed him to work out the actual energy of those charges going around. I won't go too much into the specifics of how he did that, but needless to say, it was an experiment to explore the relationship between the light shining onto this photocell and the actual current that is as a result. Now, what happened was this, okay? Leonard fired a weak ultraviolet source, and he expected, of course, when you fire a weaker source there, you'd get a slow electron. So therefore, if he were to apply a strong UV source, he thought, well, strong UV source, the electrons would get faster. In other words, the intensity, he said, well, literally, if I increase the intensity of my UV source, then surely my electrons would have more energy. More intensity means more energy. And so he predicted fast electrons. But unfortunately, that's not what he observed. What he observed was that when he increased the intensity of the UV light, he discovered that there were more electrons released, but they were no faster, which is really odd because he was expecting that if you fire more, one for a better word, more energy at the substance, surely some of that energy would be converted into kinetic energy of the electrons. But that's not what happened. And he was really at pains of how to explain that. Why increasing intensity should be increasing energy, and increasing energy should therefore translate to increasing energy of the electrons. And he could not explain that. So it was a real problem. This experiment that he set up caused real problems in understanding the wave nature of light. And so, increasing intensity and not the wavelength seemed to have should have caused an increase in electron energy. So now we actually have three particular observations that were really a conundrum for physicists at the turn of the century. We had, of course, Hertz's experiment over here, where certainly the presence of UV, or at least altered the length of the sparks over here, which he observed as what we now know as the photoelectric effect. We have the problem of Planck, and that the mathematics solution will give us dots along our curve, but it could not be explained in terms of their understanding of waves, of light. And then there was Leonard's experiment. So we have these three separate experiments or thoughts that didn't have a solution. And of course, what happened was in the early 1900s, we have Max Planck's and Leonard's and Hertz's work being interpreted by this guy over here. And this guy, of course, is well known. And this is a very young looking Albert Einstein. And Albert Einstein put it all together, and that's really what his genius is. So let's explain what he suggests. So he said, look, okay, there's light shining on metal, and we know that electrons are liberated somehow by the shining of light. Okay, and we call these photoelectrons literally because they are electrons released by light, and photo literally means in the Greek light. So the shining of light on a metal causes electrons, and it seems to be that for UV light it works well, but it's hard for red light. So somehow the frequency is definitely affecting the ability to liberate electrons. So what he says is this: well, how about we treat light, as Planck suggested, as actually in a particulate form? That is, it comes in discrete amounts. And these, what we now know as photons, have a specific wavelength and therefore a specific frequency. And he suggested this, that the energy of the photons contributes to the release of the electrons. In other words, each of these photons here have an amount of energy. And increasing the intensity of the light only increases the amount of photons. So the idea is that if this guy here has a certain amount of energy over here, right? So a certain amount of energy, that energy is equal to its HF. Now that energy will determine whether this electron gets released. Now, if this energy is too low, that electron won't get released. But if it's high enough, it will get released. Anything that's left over will contribute to the electron's kinetic energy. What Albert Einstein also suggested is that there is a one-to-one relationship here, so that for every photon that arrives at the metal, one photon contributes to one electron. That actually explains Leonard's observations. Increasing the intensity basically means increasing the number of photons. That means an increasing number of electrons being released, and therefore that means an increasing current. However, the important factor is that the energy was actually not related to the number of photons. The energy is related to the actual initial energy of this photon. So in other words, the higher frequency, e.g. UV, would contribute the fact that this electron will be released from the surface and therefore have some kinetic energy. If the frequency is lower, then possibly any leftover energy will be less, and the electron's energy will be lower as well. And in fact, if the S electron is bound by this metal to a certain degree that this energy isn't enough for this to be released, then no electron is released at all. So what I want to do now is I would like to show you this in more detail using an animation from PhET to explain this concept. So here I have an animation from University of Colorado PhET site, and in this I want to explain briefly in terms of how the photoelectric effect works. Now this is a similar setup to what Philip Leonard had set up. So we've got a voltage supply. By setting the voltage supply, he could determine the energy values of the flow of charge that went between the two plates, and the current measured, of course, how much charge flowed. And what happened, of course, is that I'm going to move this to a frequency or a wavelength of around 577 in the yellow. And as I increase the intensity of the light, you can just barely see the light hitting. But as you can see, nothing happens over here. And so what we do is we do what Leonard did. He actually started to move, use light that was closer to the UV. And so you can see here electrons being emitted, and then we establish a current. Now he surmised that if I altered the intensity, then the intensity should increase the value of the actual energy of these electrons. But if you notice carefully, these electrons aren't actually going any faster. Now, the way he measured, of course, the energy was by putting a potential difference across this. But needless to say, what he noticed was that if I were to increase the intensity, you can see that the current increases and the current decreases as I play around with the intensity. But the actual speed of the electrons, and don't worry about these guys are, because I played briefly with the value over here, but you can see that the speed remains constant, and he couldn't explain that. So what Albert Einstein suggested is this. He said, well, okay, let's choose that these are actually photons. And so the photons here contribute basically to the two things. First of all, the number of photons here determines the number of electrons being emitted. So by changing the intensity, all I'm doing is changing the number of photons. And of course, I've got a few photons, and I'm only going to get a few electrons released. And as a result, you can see the current is, well, in this case, is quite low. And if I increase the intensity a little bit, you can see that the current starts to increase. Okay, so that's fine. But the actual energy of the actual electrons is basically due to how much energy these individual photons have. So if I were to increase the frequency or decrease the wavelength, what would happen? Well, it means the energy of the photon increases. It means there's more energy left over after the energy's been used to make the electrons overcome the attractive forces on the material, and then these guys will go faster. So here we go. So I've increased the intensity, and all of a sudden you can see these guys are going faster. And again, by applying a potential difference across it, that you can actually measure the amount of energy onto that. If I increase the intensity, I increase the number of photons, but I actually don't increase specifically. You can see the current increases, but I don't actually increase the actual energy values. If I push it up, of course, into a higher, there you can see all of a sudden I'm releasing a lot more. Now, of course, the reverse is true too. If I go back down, all the way down to, let's say, yellow, what you can see now is that even though I've got a really high intensity of yellow light, the actual energy values of these guys is actually not enough for the electrons to be liberated. And that's the key thing. The energy of each electron is only determined by the photon's energy, which is HF. Now, if I were to graph that, I would get this. So here is an important graph. Okay, so what I've got here is a graph with energy and a graph of frequency. And if you notice that if I leave the intensity about 80, as I start to move across, you can see this dot represents the frequency increasing. But at this stage, I've got no electrons being emitted. But there comes a point in time I now start to get electrons being emitted because the energy now is just enough to release the electrons from here, giving a little bit left over for them to have some kinetic energy. If I continue this process along, you can see that the line continues to rise like so and go up. So what's going on? So what's going on? So the energy of the photon is equal to HF. Right? But that energy is being absorbed by the electron, and that energy that is needed for it to release is called the work function. So what we do is we subtract this work function and we call this W. But in reality, that work function, H, okay, there is equal to H multiplied by the minimum frequency needed for it to be released. That's this value right there. And that is called the threshold frequency. Now you can clearly see that if I do this mathematically, I will have something left over. And that is equal to the kinetic energy of the actual electron. So you can see if the photon's value in terms of energy is less than the minimum required to release, then I'm going to have no kinetic energy. In other words, if I move this, get it down like so, there comes a point in time where that energy is not available, and so as a result, I have no electrons being emitted whatsoever. But if I increase the frequency, like so, you can see that now all of a sudden I've overcome the work function and I have some kinetic energy left over. Notice though, if I increase the intensity or decrease the intensity, that doesn't change this relationship whatsoever, because the intensity just determines the number of electrons, and so therefore that determines the current. But it does not affect the actual energy of the electrons. Now, I've been playing around with this a bit, that's why there's a slight different speeds over here. But generally speaking, what's going to happen is that ultimately the only thing that contributes to the energy of the electrons is the frequency of the photons that I use. So let's, in summary, talk a little bit about this graph. So we've talked about how an electron is released due to the fact that the electron's energy is equal to HF. Now here's the photon's energy over here. Okay, and that is basically this particular value down here. I'll just move this up a little bit so it's a little easier to see. Now, then the energy, the minimum energy that is required for the electron to be released is referred to as the work function, and it is actually due to the fact that that work function, so that's this over here, the work function, is equal to Planck's constant multiplied by this F naught, and that F naught is called the threshold frequency. Okay, spelling here. Okay, so and then the remaining kinetic energy is as a result of the difference between those two values. So, in other words, if I were to therefore draw a graph that represents this as I increase the frequency, you should be able to recognize that this is actually a linear function. So we've got here y is equal to mx plus b. And so if we work that out and we actually graph that, well, then what we get is a graph that looks something to the effect like this. And what's happening there, of course, is that this here, this point here, represents that threshold frequency. Okay, the slope here can clearly be seen as equal to h, which is Planck's constant. Now, of course, if we drag this particular point down over here, we actually get the energy value of the work function. It's actually the y-intercept over here, but we will just start the graph from over here. Now, remember, where this is dependent on the material. So, for example, if I have a material that has a stronger work function, aka I have a material like platinum, for example, well, then its work function may actually be somewhere over here, or its frequency related something over here. But the most important fact is that the graph will be identical in that the slope will be the same. It's still the same value. It's just that the y-intercept has changed. And if I then have a substance that is a little bit further across, so in other words, even a stronger work function, then that graph may actually be over here. But again, the most important feature is that the slope is the same. So this is a very important graph for you to understand, that the graph of the kinetic energy related to the frequency of the photons, the kinetic energy of the electrons, and the frequency of the photons that arrive is a linear graph, and whose slope is always h. So I hope that gives you a good understanding of the photoelectric effect. Thank you very much. I hope you found that video useful. And remember, like, share and subscribe. Oh, and if you have a comment or a question, or you'd like a concept for me to explain to you, please drop a comment down below. I'm Paul from High School Physics Explained. Bye for now.